Welcome to everybody to our webinar today. Our webinar today will be given by Mariana Vertenstein, that she's the, too many things, but she's the responsible of the CESM system group at the NCAR. She also has a PhD from Harvard. And she has been active in this area for many years, and she's also on a number of different boards at INES in Europe, and also at the Norwegian Earth System Modeling Group, I think. And Mariana today will talk about the infrastructure that they've set up for the couple Earth system model system. That is a hierarchical, flexible, and modular environment that allows to different models interact in a very innovative way, I think. So I would like to thank Mariana very much for the time that she's taking to talk to us. I will just have a few slides to give you a short introduction of CMCC, and then I'll give the floor to Mariana. CMCC is a foundation and a research center that has been set up in Italy to study the issue of climate change from the design of the numerical model all the way through the impact analysis, scenario and prediction studies to the impacts on policy and the society and the economic consequences. So we are really the tasked to consider the Earth system together, the physical part and the social and the human part. We are a network. Our headquarters are in Lecce, in the south of Italy, and that's where we have our supercomputer that is dedicated to all our numerical effort. We have large offices in Bologna, Venice, Milan, Viterbo, Caserta, and Sassari. We're currently about 200 people. We're organized in 9 research divisions that, as I was saying, covering all the aspects of climate and meteorological research, from scientific computing through the climate simulations, ocean modeling, data simulations, impacts on various sectors in agriculture, forest, ecosystem, and then going on to risk assessment and adaptation strategies, economic analysis. We also have effort on regional models and hydrological impacts on land. And we have organized together with one of our founding members, RFF, Resources for the Future in Washington, the European Institute of Environmental Economics that is set between Milan and Venice, that is also working on the economic analysis and the sustainable Earth modeling, economic modeling. So we are a sort of wide range of topics that we don't do only fundamental foundational research. We're also doing applications in a number of areas. We do predictions. We're heavily involved with the Copernicus program in Europe and in the IPCC, in the integrated coordinated scenario experiments that go into the various IPCC reports. And of course, we have a large outreach portion of which these webinars are a component, and we do publication, events, and other things. So after during the seminar, your audio and video will be deactivated. And if you want to ask a question, you can actually raise hand at the end when there will be a question, or you can write it in the Q&A section. And I think that oh no, I have to say that the webinar will be recorded and uploaded, so there will be a YouTube channel in which there is this thing, and any other information can be sent to the email you see here. And of course, you're welcome to look at our website at www.cmcc.it, where there are a lot of other information. And with this, I think that I want to conclude and just inform you this is our next webinar in our next series that is about about COVID-19. Okay, thank you very much. I think I can give the screen, not the floor anymore. So I'll give the screen to Mariana.
Okay. Can you see?
Mm-hmm.
Okay. Thank you, everybody, for joining this webinar. I really appreciate Antonio's invitation to be able to present to you, because we have been doing a lot of what I consider exciting new infrastructure improvements that will be really important for the next version of the Community Earth System Model Next Generation System. And in addition to me, Mariana Vertenstein, I'm the head of the CSM Software Engineering Group. I've also invited Brian Dobbins and Rocky Dunlap, who are also on this call. And Rocky is the head of the framework group that I will be discussing called ESMF NUOPC. I'll go into details about that. And Brian Dobbins is an expert on clouds and containers and has also recently joined my group. And so any detailed questions regarding that, they're on, and we could also have follow-up discussions with them. So what I want to talk about today really is in 5 categories. I'd like to first outline what I mean by our coupling framework that permits new flexible coupling between components. And that's our system modeling framework, NUOPC. I'll talk about that in a minute. And given a description of this framework, I also want to talk about our new implementation of the framework called the Community Mediator for Earth Prediction System, or CMEPS. I have to apologize in advance. There is a lot of shorthand notation that I'll be using, CMEPS, CDEPS, and I'm trying to define each of these very carefully, but it can be a little bit overwhelming. In addition, what we feel very strongly about is that you should be able to flexibly turn feedbacks off and on in your system, which I call hierarchical model development. And we have a new set of sophisticated data models that also use this ESMF NUOPC framework called the Community Data Models for Earth Prediction Systems, or CDEPS. And finally, you now have this coupling between components, hierarchical model development. We also have a Python-based workflow system called the CIME Case Control System, which enables you to use both CMEPS and CDEPS along with your prognostic components very flexibly. And finally, containers in the cloud are on everybody's horizon right now. And we've made real great strides due to the work that Brian Dobbins has done to do what we call CSM everywhere, new capabilities to run CSM both in containers and on the cloud. And I'll be summarizing that as the very last topic I'm discussing. So the first question is, what is ESMF NUOPC? So ESMF stands for the Earth System Modeling Framework, which is a community developed and governed software for building both numerical weather prediction systems, climate systems, and a whole range of Earth modeling applications, regional and global. And it provides you with both standard component interfaces, and standard is important because once you standardize things, you can have different groups collaborate using these standards like the APIs. But it's also high performance, and the high performance enables you to effectively connect models. This is very important, carry out runtime regridding between components, along with optimizing parallel communication. And what ESMF did a few years ago is they created a layer on top of ESMF, and this is a mouthful, the National Unified Operational Prediction Capability layer. And it comes with ESMF, but it introduces new generic components that simplify the interoperability of using ESMF components by adding yet more standardized coupling protocols. And these new components, as I'll talk about, are drivers, connectors, models, and mediator. So the important thing to know is that ESMF NUOPC is in fact has become the de facto coupling infrastructure for a UFS modeling system. It's used by NOAA in their new, what they call the Unified Forecast System, where they are integrating many applications into a very small set of 9 applications, all using ESMF. It's used by the Navy for regional modeling. It's used by NASA for their GEOS 5 modeling. And what I'll focus on today is that we are moving to use it solely as our coupling infrastructure for CSM moving forward. So you have 4 different US agencies that are all committed to using and leveraging ESMF NUOPC, and this ability to use the same framework opens up completely new avenues for collaboration that were not available before. So I'll start off with coupling between components, and that's achieved by our new Community Mediator for Earth Prediction Systems. And what we are planning for is to target a new release of the Community Earth System Model 3 in a few years from now. And we're doing incremental releases till then. We've just released CSM 2.2, but what we are targeting is that as of CSM 2.3 and moving forward to CSM 3, we will be focusing only on ESMF NUOPC as our coupling infrastructure. So I want to give a quick overview of where we were before to show you the improvements of where we are heading towards. So in the Community Earth System model, we have 7 components of the Earth system: an atmosphere, an ocean, a land ice, a sea ice, and a wave, and also what I call external system processing. These only communicate with each other via communication in a hub and spoke type architecture with a central hub. And the way they do this is that they exchange data with this hub, and then the hub does things like merging and mapping to then send data to the from a set of source components to the destination component. I think what's important is that in the past, we had what was called a DOE developed model coupling toolkit for the last 15 years that did a lot of this merging and regridding, but it used basically offline generated mapping files and ingested those and then did the mapping and merging. One of the key aspects of this architecture is that you have a very lightweight cap at the top of every component software stack, and that cap is responsible for translating internal data structures of that component to the coupling infrastructure data structures and then translating it back. And another key aspect of this is that the way we did this architecture is that we had data components for every single prognostic component, and that data component can be switched from the, in terms of the coupling infrastructure. You can substitute the data component for the prognostic component and thereby snip feedbacks off very flexibly in the system. And the coupling framework is ignorant of what type of component you have on the other side. It just knows that it's receiving and sending data to that target component. So that's where we were before. One problem is that there was really no separation between the driver that controlled the temporal evolution of the system and the hub that was responsible for doing the mapping and merging and effectively data mitigation through the system. So what are we introducing that's different? We're replacing the hub and the connectors and the cap from using the model coupling toolkit, which was a very lightweight Fortran code that hasn't really been developed a lot over the last several years, with NUOPC in terms of this new implementation using ESMF NUOPC called CMEPS. And the only difference, as you can see here, is that instead of having a model coupling toolkit cap on every component, you now have what's called a NUOPC cap that does the same type of translation layer. The thing is that the CMEPS infrastructure, then what we call the mediator, is not just being used by us. It's actually now a public, in a public repository on GitHub, and it's being leveraged both by us at this point and by NOAA. And so many different types of components, other than just the CSM components, can interact with the CMEPS mediator. And the Navy system is also starting to explore whether they want to use it. And in ESMF NUOPC lingo, this hub here is called a mediator, not just a hub by itself. So what is in the CMEPS name? It's community because right now it started off being developed as a collaboration between NCAR and NOAA. It's open development on GitHub, and as a result, we have community code contributions that can come in. The mediator for the M is a NUOPC-compliant coupler, and the whole idea is flexibility and extensibility to be able to couple different configurations of a variety of Earth system model components using a hub and spoke architecture, and also permit hierarchical model development. And finally, the Earth prediction systems. CSM is moving more and more towards also looking not just at long-term climate applications, but sub-seasonal to seasonal applications. And so currently we're using CMEPS moving forwards for community Earth system model experiments, but also the NOAA Unified Forecast sub-seasonal to seasonal application has adopted it and has moved it to operations. And currently we're working with NOAA in terms of their new hurricane analysis and forecast system, which will also be based on CMEPS. So I wanted to now delve a little bit into the details of CMEPS to outline what are its huge advantages in terms of leveraging it for Earth system models. So NUOPC provides these 4 new different types of components. There is the driver that controls the temporal evolution of the system, and it now has a data-driven run sequence. And this is really amazing. I'll show you a picture of it. The mediator itself is another new component that NUOPC has introduced, and CMEPS is just an implementation of a NUOPC mediator. And one key thing is that the mediator does parallel online generation of mapping weights for a variety of different types of grids. As a result, you no longer have to create these mapping files offline. So it provides tremendous new flexibility for introducing new meshes into your system, whether they be regional meshes or global, regionally refined meshes. And finally, you have these connectors that connect your component to the mediator. And a very powerful new feature, that ESMF NUOPC has introduced is that these connectors in green are actually automatically generated for you. You don't have to write any code for them. And they have a lot of optimization options, including reference sharing and component level threading. So here's an example of where runtime generation of mapping weights is going to be helpful to us. We're exploring a whole set of new bulk dynamical cores in CSM, along with a wide variety of new regionally refined grids. And ESMF will give us the flexibility to generate runtime mapping weights for these systems, and also provide second order conservative mapping, along with bilinear, nearest neighbor, first order conservative, and a plethora of other types of mapping weights. So one new feature of the ESMF NUOPC is that your run sequence is now just a very short ASCII file that generates the ability for the driver to create the entire run sequence at runtime from the small file. So currently, the MCT Coupler 7 system had several thousand lines of inline code that generated the run sequence. And trying to understand it, or trying to understand what was happening for different scenarios, including The fact that at some point you had no feedbacks or data models was extremely difficult. With CMEPS, your run sequence is automatically generated using this small ASCII file, and it has a very simple syntax. So instead of several thousand lines, you now have just a few tens of lines to describe your entire run sequence of the systems. The components can have different coupling frequencies. They can have multiple named phases, and a very powerful thing that your run sequence can be changed at runtime without recompiling, and this permits both sequential and concurrent execution of components. So what I'll describe here is what the simple syntax is. Sorry. This number here tells you how frequently you want to couple this particular phase. And so in this run sequence, you have 2 coupling intervals every half hour, every 900 seconds. When you see an arrow here, that means send data from the mediator to the atmosphere components, just simply using redistribution. And just seeing this run sequence, ESMF creates this connector to transfer data between the mediator, the components, and there is no user code that needs to be done. And as you can see further down below, these are just different run phases of the mediator, where you can prepare data to be able to send to the ocean, accumulate data. And then of course, if you see this line here that just says ocean, that means run the ocean on its processor set. And as I mentioned before, you can decide how you want to lay out your multi-component system across processors. And this run sequence and ESMF NUOPC will know how to call these components only on their own processors, how to exchange data between them. Another thing that we're actively working on is how to do data assimilation using the new JEDI system that's being developed, which is the Joint Effort for Data Assimilation Integration, by simply having a new ability to layer the data assimilation system on top of our NUOPC driver. And one thing I want to emphasize is that the mediator can be shared between components, but the driver is really model specific. And there is a new implementation that ESM is working on in conjunction with JEDI so that you can keep all the advantages and the complexity of your coupled model system using ESMF NUOPC and transfer the ESMF state data between your coupled model system and JEDI simply using this new communication layer that's being developed. So what is the status of CMEPS? For CSM, we have implemented CAPS on all of our prognostic components. We are currently validating it. We have created a new set of data models that I'll talk about in a second that permit you to swap data and prognostic components when you create an experiment. In terms of the NOAA Unified Forecast System, they have adopted CMEPS and transferred it to operations, and their configuration is to use CubeSphere FV3 with the MOM6 Ocean component and the CICE Consortium component as their 3 coupled model components that they use to create their Earth system model seasonal system. So as I mentioned before, there are numerous benefits to moving here. You can introduce new grids much more easily. Because you have standardization, you can unify component caps across modeling systems. If somebody develops an improvement to the model, such as WaveWatch, and it has a NUOPC cap, it's much easier to bring it in because that's where the interoperability comes in. And it's also easier to introduce new field exchanges, adding new fields between systems because ESMF NUOPC has a very sophisticated brokering system that determines how you set up these connectors and how you determine the exchanges between fields as you add new fields to the system. So what about data models? Why do we want hierarchical model development? And again, as I mentioned before, it's because we want feedbacks to be able to be turned off. And that's often the way all of our components in CSM are developed. Normally, they are developed by forcing the target component with observational data and then incrementally turning on feedbacks across the modeling system to determine what the effect of those feedbacks are in creation of the new parameterization. So we want to have the ability to easily swap those out. And again, with data models, you can also reduce the debugging time because you can isolate the components. So over the last several months, we've created a totally new set of data models. Again, these are in their own GitHub repository. They're called CDEPS. And they are new ESMF-based NUOPC data model functionality to replace the data models that were currently in CSN that were using the MCT interface. A key point is that these CDEPS data models are compatible with CMEPS, and they are also compatible with the CIME Case Control System as workflow, but they do not require a target workflow to use them. So the data models have new online regridding capability that will flexibly regrid your forcing data at whatever resolution you have to your model mesh, and includes many new regridding options that weren't there before, including conservative regridding. Another very powerful option is that you can now regrid multiple levels, so that if you want to do 3D regridding, but between two components that share the same levels, it's effectively very easy to do with the way ESMF NUOPC permits you. Another thing about the data models is that all of our I/O is parallel in the data models. It's using what we call the PIO2 library that comes, that CMEPS is assuming, but also the data models it's using. And we've introduced new modularity for science-specific data modes. So a key aspect of the design of CDEPS is code reuse. So the data models have separation of concerns for their science capabilities, but in terms of the guts of the data models, in terms of the regridding and the time interpolation and the parallel I/O, all of that code is shared. And a new capability that is going to be extensively leveraged across the CSN system is that these data model share code functionality actually can be called directly from the prognostic code base. You can have the data models themselves, or you can leverage the functionality directly from the code. And our community atmosphere model, that's the atmosphere component of CSN, will leverage this for both new nudging capability and for ingesting aerosol forcing. And in addition, the NOAA Unified Forecast System is also migrating to CDEPS for their data model functionality that they want. And I'm just going to show you a very brief example of how CDEPS works. And so with CDEPS, if you have a data model, it will want to ingest different streams, where a stream is defined as a set of fields in a file that all share the same mesh and the same temporal frequency. So what CDEPS has to do is take the streams and regrid the streams to your model mesh, and also do time interpolation of the streams. And then what the data model has to do is take these regridded streams, both in temporal time and spatial, and potentially fill in missing data or manipulate them scientifically for their target output, and then send them to CMEPS. And that's where the model field comes in. But what we have now is the ability to actually have a prognostic component also ingest the streams without it being a data model. And that's very, very important. If you would like to ingest a set of 3D data fields on a set of levels and then vertically interpolate the levels, there is a very lightweight API that goes directly into the CMEPS data model functionality to enable you to ingest that. And we're currently working to validate this and strengthen it. And as I said before, use this as the data model functionality moving forward, that CMEPS will be compliant with CMEPS. And now moving on to workflow. So before, I think there's a little bit of confusion with what we called CIME before. CIME is the Common Infrastructure for Modeling the Earth. It was developed as a joint effort between the Department of Energy E3SM model and the CSM model, where we were actually at that time sharing both coupling infrastructure and data models and workflow. And so all of that, the coupling infrastructure that I mentioned before that was built on the model coupling toolkit, and the data models that were built on the model coupling toolkit were part of CIME, along with this very user-friendly Python-built workflow called the Case Control System. But as we're moving forward, we're no longer going to be interested in those data models or that coupling infrastructure, and DOE still is using it. So CIME, as we're talking about today, is actually being split apart. And what CIME will contain moving forward is just the workflow. And I think that will make it much more flexible, because that's the part that you can use without worrying about getting a specific coupling infrastructure or data models. So when I talk about CIME right now, I'm just going to be talking about the case control system. So the case control system is a user-friendly, extensively documented workflow for configuring a complex Earth system model. The key point is you can create experiments, configure, build, and run them by invoking only 4 commands. The case control system has been written with object-oriented Python script, and it is configured using XML files. CIME Case Control is an open collaboration on a public GitHub repository, and a key point is that it's multi-agency. It is fundamental to both the NSF Community Earth System model and the DOE E3SM model, along with the Norwegian Earth System model, and now the NOAA Unified Forecast System weather application that was released a few months ago. The application itself was released to the community on CIME, based on CIME, and there is a new Earthworks model that is going to be a cloud resolving model coming out of CSU that will also be based on both the CIME Case Control System along with CMEPS and CDEPS. So the Case Control System can handle coupled models as well as non-coupled model configurations, and is easily extensible with an experiment database, and as I'll mention in a minute, also cloud and container functionality. So I'm just going to give an example of using the case control system for a weather application, because that's really the reason I'm showing the weather application and not just a CSM application, is because I want to emphasize that you can use this workflow not just for CSM. So basically what the weather application does is that you create your experiment, and this is where I have the start here, is you can create this with 1 command. You create your experiment, you create batch and system scripts for your target experiment, you build it, and then you run it. And there is new workflow capability with CIME that enables you to say, hey, don't just run my experiment, but carry out a set of dependent tasks as part of it. So the way that was done for the medium range weather experiment is that it went to a server and downloaded the relevant input data for your forecast model. And this was done automatically. It then carried out your forecast, and then it converted the native model output to the required format. And again, all of this was done with just a few subtle commands. And what was very encouraging was that Neil Jacobs, who is, for at least a very short time, the current head of NOAA, actually ran what we call the graduate student test with this, and felt that this was the most user-friendly system he's ever used, and that included WRF. So he was very positive about how easy it was to set up and carry out an experiment for the user community using this workflow. And now I'm going to wrap up my talk by talking about our next steps, which is what we call CSM everywhere. How to extend CSM using the containers in the cloud to make it truly accessible to a much wider community. So what are the benefits of containers in the cloud? The key point is that you don't have to worry about porting because you have an image that works everywhere. It's standardized and you could share workflows. The image can work on Windows, Mac, Linux, and you don't have to port it. This is, as much as we try to make CSM easily to be portable, it's still a complex system, but with a container, you totally circumvent that. And this is a very other important, it's extensible. You can add features, you can add visualization, you can add analytics, you can add Jupyter Lab. So with containers, you can use your own system, laptop or clusters, but also you can run it on the cloud, which circumvents the need for you to worry about what system you have. So why is it CSM everywhere? Because the goal is to let anyone easily run CSM on nearly any system for both small and large scale science. That's what we're really aiming for. So a little bit more about our cloud functionality is that we've already demonstrated the use of CSM on the cloud for training workshops. Example is a CSM workshop at AGU. And we've demonstrated that it can work on Amazon Web Service. We have released yet, but it's not public, but it is available by request. And a caveat is that it is good for slower runs or ensemble runs, but a challenge with clouds right now is that there are scaling issues to larger networks, but there is active work to circumvent this issue. In the near future, we hope to have a public release of the tool along with the support for the Microsoft Azure system and along with improved performance, because it appears that we will be able to also have the Intel compilers as part of the system that can then run on the cloud. And again, we would be leveraging cloud local input data stores as part of this. And then finally, here is an example of what we can do. We can download a self-contained CSM image that includes Jupyter Lab and a Pangeo stack for both analytics and visualization. And this is an example of how you can access this, give access to the community for this, and provide great training, classroom ability, and a simpler functionality of examining your model results in a standardized environment. In the near future, we hope to have an official release tied to the CSM 2.2, which again does not use CMEPS and CDEPS, but our goal is to have this all wrapped up as part of the CSM 2.3 release that will then have this ability to run containers on the cloud with CSM 2.3 and all of the functionality that I've mentioned before, including the CIME Case Control System, the data models, and the new coupling framework and mediator that I mentioned before. And with that, thank you, and I hope there's lots of questions. And as I mentioned before, Rocky and Brian are also on the line and can help answer detailed questions about this in their area of expertise.
Okay, thank you very much, Mariana. And yes, we have now, we're going to take questions, and questions can either be written in a Q&A chat, or people can raise their hands and I'll try to give them the microphone. I can see there is already one question, so I'm gonna give you the microphone. Please say your name first and then ask the question. Hello?
I think the person just disconnected.
Just disappeared, was scared. Okay. All right, so if there are any more questions? Okay, I have a question myself. This is very interesting, and I think is really going in towards the direction of making life easier, because we really have a big step, threshold in to overcome, especially for students and training that people that get into this business. So I was wondering how does this interconnect with the science development? I mean, how these developments are in somewhat connected with the discussion in the model development part, and how the transfer of new stuff is facilitated by this framework.
So the way, in terms of scientific model development, the cap that you write to be able to use this new infrastructure is very lightweight. It's actually a very small piece of code. So it doesn't go down into any of the scientific changes to the system that are being put in. So from that point of view, there's a total separation of concerns. The key point is that as we're moving to more complex systems, so say that your new science development requires an exchange of fields. So I'll give you an example. There is the current need to start transferring subgrid information from the land model to the atmosphere. And it would have been very hard to do this with the old MCT framework. I think it'll be very straightforward to do this with NUOPC. Here's another example. We need to be able to run ice sheets, both Greenland and Antarctica, simultaneously. That's something we're trying to move right now. Until now, we were just running Greenland as an ice sheet. We really couldn't come up with an easy way to do it with MCT, because it wasn't clear how you were going to pass in. We were going to create a unified mesh for the whole thing. And then what about if you want to change Antarctica, a new unified mesh? With ESMF NUOPC, it is super simple. The sophistication of what you can do to couple different meshes to the mediator from a single component is very easy to leverage. The same for being able to have coupling at multiple ocean levels with different bathymetry. So the point is that the requirements of new science are facilitated by this, but where it doesn't matter that you're using NUOPC, your scientific development can occur totally agnostic of what's happening at the coupling infrastructure level.
Yeah, that's I think is really interesting, and I have a number of questions, but one thing that I wanted to ask right away before we get into this question is, what are there any plans to do porting or using to GPUs?
So that is a question. Maybe Rocky can talk about the fact that there is the ability to have heterogeneous support at the coupling layer, but the coupling layer itself is not where you're going to want to put GPUs. But Rocky, do you want to mention what has been done?
Yeah, can you hear me okay?
Yep.
Sure, go ahead.
Great. Yeah, I agree with you, Mariana. There has been a little bit of work in ESMF to recognize the availability of accelerator devices, such as GPUs, on HPC nodes. At the current time, that is not to actually run any of the coupler or the mediator on the GPUs. The purpose of that is when you're laying out a set of model components, you may have some components that can leverage a GPU. Say the atmosphere, maybe the physics has been ported to the GPU, but you're coupling with an ocean model, which is purely MPI. You need to intelligently lay out those components on the HPC system so that the atmosphere is sitting on the nodes that has the GPUs. And so at the coupling framework level within ESMF, it's important to be able to negotiate at the beginning. Here's a set of nodes. How do I want to lay out my components on the hardware? So that's one aspect of it. An aspect of it that is, I think, on the horizon is as multiple components are ported to GPU. Say you have a atmosphere, ocean, ice coupled system, and those three components are able to leverage GPUs. Now, when it comes to coupling, you might want to be able to directly move data from GPU to GPU without going through another memory hierarchy. And so as we start moving in that direction, the coupling framework is going to have to become more aware of memory structures potentially, to make sure that there's not redundant copies and that sort of thing. To date, however, we're not seeing that that is typical. I think people are branching into GPUs. A number of components are starting to be able to leverage it. But by and large, the coupling layers are not terribly expensive right now. And so there's less impetus to begin porting some of that part to the GPU just yet. But it may be coming in the future with very high resolution grids where for the interpolation aspects or the neighborhood search, we might want to leverage the GPUs at that time, but it's not something we're doing right now.
Okay, thank you. And I have another question. Stefani is asking how easy it is to create new interfaces to couple other models like ocean models, for instance. Is the workflow able to monitor the task execution and be integrated in the HPC environment?
Okay, so I think they're two separate questions.
Yeah,
I'm not sure I understand the second one, but
me too.
How easy is it to create a coupling interface? It depends on the complexity of your system and how much you can expose at the top level. Mm-hmm. I think if we think about what was done with NEMO, you've already done the hard work because you coupled it to MCT. Translating that to NUOPC would be very simple because you figured out how to, recognize and listen to signals like it's time to write a restart, or I'm going to give you my grid. For a completely new system, it depends on, again, you need to be able to say, if your system is fairly isolated, it's a component by itself already of a coupled model system, I don't think it would be a huge task. If it's a subroutine call in another system, like, okay, they're interested in separating the NOAA land model from the guts of the current atmosphere model as a separate component. That's not easy because you don't have a separate component. You have to actually start from scratch to create that component. But I would argue that that's not the hard part is not writing the interface for it. The hard part is creating a separate component for that and making it, standalone capability. So I would say that the act of just creating a new NUOPC cap is not prohibitive, particularly because there's so many examples out there already today.
Yeah, in fact, this is the same issue when I remember we discussed the issue of trying to separate the physics in the atmospheric model as a separate component and then couple it so one could switch physics up and down. That's of course a very difficult problem because they're so tightly coupled with the rest of the code that it's not so easy. And also I'm not sure it would be tremendously efficient if we put some sort of interface between the physics and the rest and the dynamical core. So I don't know, but it's obviously not simple.
Yeah, it depends on what you're trying to do. And it's interesting because NASA has developed their system as a whole hierarchy of ESMF. And that's running very effectively. I mean, it's all the way down. Every different part of the system is an ESMF gridded component.
Against which radiation, for instance?
I'll ask Rocky to answer that.
That's correct. That's correct. If you think about dividing your physics up into a hierarchy and picture what that would look like, that's what the GEOS model, that's the architecture that they've decided. So they have fine-grained components such as radiation, land surface, runoff, and that allows them to interchange those a little bit more easily.
Yeah. Thank you. I think I have a very easy one for you, Mariana. Daniel is asking if CESM is open source.
Yes.
Yes, that's it.
That was easy, yay.
That's easy. That's easy. And he's also asking, well, that's, I don't know what, okay, I'm going to ask you anyway, if the CESM can be used to study the impact of sea level rise on mangrove ecosystem. I don't know if anybody has done that, but probably, I'm not sure. So
I think that's a science question. Yeah. So everything I've talked about is plumbing.
Yeah.
So how you choose to create what you want to plumb together, that's the plumbing in many respects is, I hate to say the easy part, but it's the straightforward part. The true incorporation of the science is the challenge. So
I think the one other answer is to say, look, here there are all the toolbox, and you can go and study the mangroves, basically.
Exactly.
Yeah. Okay, and Fabio is asking, which models have been tested as prognostic component? Well, I guess all of them.
Well, okay, so we have a lot. In terms of prognostic, are you talking about with CMEPS or are you talking about with ESMF in general?
I don't know. It doesn't say.
Okay, so for CSM, we have the atmosphere component, which is CAM, the land component, which is CTSN, the ocean component right now is both POP and MOM6. The land ice component is CISM, the wave component is WaveWatch 3. For the UFS, they have the FV3, the UFS atmosphere. They're also using MOM6. The ice component is size. I could go on and on. These are just labels, but there's a lot.
There is another question that I think has been partially answered. Giovanni asked how difficult it is to change version of a model that is already been in the system. So I think that will be really quickly, really fast. Once you simply change a version, all the interfaces are set, so there should not be.
Yeah, and many times actually, if the data structures haven't changed radically, I can update the model and it just updates. Yeah. You haven't touched the interface, it'll just work.
And George instead is asking if the system can actually, she's talking about CIME, but you know, see what you can do, can be used also for regional.
Yes. Yes, and that's the example that we're working. Actually, Rocky has some people on his team working on coupling a regional hurricane system to a regional HICOM. And we've explored using the CDEPS data atmosphere as a way of doing development for that, and it's all regional.
So maybe she can get in touch with you guys and maybe, you know, get more details.
Right, right.
Yeah, okay. All right, I think I finished all my questions. Time is almost up, so I don't know if there is somebody that has some last burning questions. Hurry up to write or raise your hands.
So please, we can always arrange a follow-up meeting. The reason I wanted Rocky and Brian here is because Brian has done some really amazing work where it makes the system very easy to use with containers and clouds. And without Rocky's leadership on the ESMF core team, none of what I have talked about would have occurred. So I think, you know, I can put you in touch with either one of them if there are questions regarding containers
we
and
will be in
clouds.
touch, and I would like to thank Rocky and Brian for taking the time this morning, early morning. So that will be a good idea. So people get to know each other, and, and yes, we'll definitely be in touch. So I don't see any more questions. So maybe, oh no, there is another one. Oh, Nadia is asking if we can use this framework to integrate machine learning tools on outputs. Can
I don't, okay, we're exploring machine learning. I think to me, the output, that would be part of the workflow.
Yeah.
And that would also be, I think, where containers in the cloud would facilitate doing that. So I don't see why. It just depends on how would you do it? What could you use from the toolbox that I've presented that would facilitate doing this?
Okay, I think we will need to let you go, guys, and we'll definitely be in touch. Thanks again. It's been a wonderful
Thank you.
and very useful, and have a great day. Ciao.
Okay, thank you. Bye-bye.